that no human being has ever visited. No one has ever seen this place. Yet what happens here affects every one of us every day of our lives. It's 2,000 miles beneath our feet, the Earth's molten core. Here, a vast ocean of liquid iron generates an invisible force field, the Earth's magnetic field. It surrounds the entire planet, cocooning us from the dangers of space. But now, scientists have made an alarming discovery. There's a storm brewing deep within the Earth. A storm which could destroy our vital magnetic shield.
The Earth's magnetic field has been our protector for millennia, and now it appears it's about to go away.
The Earth's magnetic field is getting weaker rapidly.
We cannot guarantee that the magnetic field of the Earth is still going to be there 1,000 years from today.
Is our invisible shield about to disappear?
The question is not if that's going to happen, it's when that's going to happen.
Could the Earth really lose its magnetic field? And what will happen if it does? Searing heat, crushing pressure, and 1 billion trillion tons of molten iron. These are the conditions at the center of the Earth.
This is the Sparrows Point blast furnace for Bethlehem Steel Corporation, and this is as close to the environment of the Earth's core as we have here on the surface of the Earth.
The Earth's core will always be inaccessible, but as geophysicist Peter Olsen knows, its influence extends over the entire planet.
About halfway to the center of the Earth, we reach the true heart of the Earth's core. An immense, molten sphere of liquid iron, and that's where the Earth's magnetic field is generated.
But recently, scientists have detected a problem at the center of the Earth. It seems the core's ability to generate a magnetic field may be faltering.
Today, something very strange is going on with the Earth's magnetic field. Its strength is rapidly decreasing, so fast that at the current rate, it will last only into the next millennium.
The discovery that our magnetic field is rapidly disappearing has prompted intense scientific research around the globe.
It's quite surprising how little is understood about the Earth's magnetic field and how it's generated.
It was a very intriguing problem, something that was screaming out for an answer.
I often wished I could see the magnetic field. I'm motivated by the mysteries that are there.
As scientists grapple with the complexities of magnetism, they realize that what is happening at the center of the Earth could change our world for generations to come. Magnetism is the Earth's forgotten force. We all feel the pull of the gravity our planet produces, but most of the time we are oblivious of the magnetic field which the Earth also generates. But space scientists like Andrew Coates know just how important it really is.
Magnetic field extent is really huge. The biggest thing really we have on Earth.
Magnetism, like electricity, flows. It's generated deep in the Earth's core, and streams out near the South Pole, loops around the planet, and then flows back into the core via the North Magnetic Pole. This is the Earth's protective force field. Without it, we'd be in trouble.
It protects us against radiation from space. It's a little bit like being in the pod here. This shields us from the weather on Earth. The magnetic field of the Earth shields us from space weather and space radiation.
Space weather is nasty. The winds that blow through the galaxy are winds of radiation, some of the most harmful, from distant exploding stars or collapsing black holes.
But there is another source which is much nearer, which is our sun. The sun itself is a thermonuclear furnace, and this flings off huge amounts of dangerous material in very large explosions. In some cases, it's about the same mass as Mount Everest actually coming towards us.
Every few hours, the sun ejects billions of tons of electrically charged particles, the solar wind. Often the Earth lies directly in the path of this onslaught. But magnetism deflects charged particles. This means the solar wind is unable to penetrate the Earth's magnetic shield, and so flows harmlessly around the planet. The only signs of this drama far above our heads are the northern and southern lights, aurora, caused when solar particles trapped in the Earth's field are dragged through the atmosphere towards the poles.
Now, we're lucky on the Earth we have the magnetic field which deflects the particles and protects us. But if we lost the magnetic field, there would be nothing to stop the radiation bathing the whole of the atmosphere, and the effect would be much more dangerous.
But just how dangerous? What would be the ultimate consequences for planet Earth if the magnetic field were to disappear altogether?
5, 4, 3, 2, 1. We have ignition.
The disturbing answer has become clear only recently.
And we have liftoff of NASA's Mars Global Surveyor as America begins its journey back to the Red Planet.
In 1996, NASA sent a satellite to Mars.
Mars has been a difficult planet to get to with spacecraft. Even after 16 missions by US and Russia and so on, we still did not know whether Mars had an intrinsic magnetic field or not.
The Martian rocks.
It was this long-standing question which Mario Acuna and his team from NASA hoped they would finally be able to settle. But what they actually discovered was something far more significant: the connection between magnetism and life.
Nature had big surprises for us beyond our wildest expectations.
As Mars Global Surveyor started to send back data, it soon became clear that today Mars has no overall magnetic field. But the satellite also detected signs that in the past, things must have been very different.
We found these huge magnetic fields in the crust, and all of a sudden a completely unexpected and unknown planet, in a sense, emerged.
Although there was no magnetism coming from the core of Mars, strangely, large areas of the surface were strongly magnetic. The Martian crust is mainly made of frozen lava, a remnant of the time when Mars was covered with volcanoes. And there's only one way that volcanic rock can become magnetized. If molten rock cools in a magnetic field, iron-based minerals in it can pick up that magnetism, and the resulting solid rock will itself be magnetic. So the fact that there was magnetism in the Martian crust proved that when the lavas first erupted, Mars must have had a global magnetic field.
And not only that, at an intensity which is 20 to 30 times that of the Earth.
So that's basically similar to Earth.
Mario's team now knew that Mars had once had a magnetic shield, which it must at some point have lost. They began to wonder whether this might be the solution to one of the great mysteries of the solar system. Scientists suspect that the young Mars was in many ways an Earth-like place, with a thick atmosphere and oceans which may have harbored primitive life. But then, around 4 billion years ago, the planet entered a catastrophic decline. Gradually, the atmosphere and oceans of Mars mysteriously disappeared.
The puzzle was, where did the water go? What process could have caused the loss of water?
Mario realized that two dramatic events in the early history of Mars might lead him to the answer.
We found two very large impact basins in the southern hemisphere of Mars, which are Hellas and Argyre. There was absolutely no magnetization over them.
In these basins, formed when two huge meteorites hit Mars, the rocks were strikingly free of magnetism. And that was odd, because the huge impacts must have melted the crust. And as it cooled again, the rocks should have become magnetized by Mars' strong magnetic field. Yet there was no trace of magnetism in Hellas and Argyre.
Which immediately meant that they were formed after the magnetic field of Mars has ceased to exist. And the estimate is that these impacts took place more than 4 billion years ago.
4 billion years ago is the time when Mars was beginning to lose its water and atmosphere. Mario believes that this must be directly related to the loss of Mars' magnetic field.
If we shut down the magnetic field, then the solar wind has direct access to the atmosphere of Mars. Then we have a process which is equivalent to the erosion in the desert. The wind blows and it blows the sand away. In this case, the sand are atmospheric particles. Slowly but surely, the atmospheric gases, which includes water, are carried away and are lost to Mars.
The loss of its magnetic shield meant death for the red planet. Exposed to the wind of radiation from the sun, over millions of years its atmosphere was gradually blown away, leaving the sterile world we see today.
If we were to turn off the Earth's magnetic field, the same process would occur. The atmosphere of Earth would be exposed to the erosional effects of the solar wind, and it would be slowly carried away.
The fate of Mars suggests that without the protection of its magnetic shield, the Earth too would eventually become a dead planet. Which makes it all the more disturbing that our magnetic field is disappearing so rapidly. Early in its history, the planet Mars lost its protective magnetic field, and with it, its ability to support life. But now, scientists have discovered evidence that our own magnetic field is in rapid decline. Evidence that comes from vanished civilizations. People have been making pottery for thousands of years. Archaeologists have learnt a lot from pots. But these vessels have another story to tell.
Pottery acts just like a magnetic tape recorder. It records the Earth's magnetic field when the pottery is first made.
An ancient pot is a magnetic time capsule. John Shaw has learnt how to extract from it a precise measurement of the strength of the magnetic field as it was in antiquity. Like volcanic rock, clay contains iron minerals, which make it very slightly magnetic.
Now the interesting part is when the pot's fired.
The key thing is that the clay is intensely heated in the kiln, and the high temperature erases any existing magnetism. Then, as it cools, the clay is remagnetized again by the field surrounding it at that moment. So every pot contains a record of the Earth's magnetic field at the time and place it was fired.
So if we take an ancient pot like this one, which is from Peru, when it cooled for the first time, it cooled in the Earth's ancient magnetic field, and it became magnetized in that field. And of course, if the field's very strong, then the pot's strongly magnetized, and if the field's very weak, then the pot's weakly magnetized.
By examining pottery from prehistory to modern times, John has discovered just how dramatically the field has changed in the last few centuries.
When we plot the results from the ceramics, this is what we see. Gentle changes as we come forward in time over 12,000 years, a gentle rise, and then a rapid fall as we come towards the present day. The rate of change is higher over the last 300 years than it has been for any time in the past 5,000. It's going from a strong field down to a weak field, and it's doing it very quickly.
In 300 years, the field has fallen 10%. If the decline continues to accelerate, it will be gone altogether in just a few centuries. So is the Earth going the way of Mars? There's only one place to look for an answer: the inaccessible region where the field is generated, the Earth's core. But with no way to get there, Professor Dan Lathrop is playing with fire as he and his students try to build the Earth's core in their lab.
Yes, that heater wiring looks pretty good.
Their idea is to find out just what keeps the magnetic field going and what might cause it to disappear. They have to model the liquid metal core with sodium because it's much easier to melt than iron.
What you're looking at here is a sphere which contains about 110 kilograms of sodium. When we run an experiment, we'll start spinning this ball like the Earth is spinning and make measurements of magnetic field that it generates on its own.
What they're trying to create is a self-sustaining electromagnetic dynamo, because that's what they think the Earth is. Scientists have a theory about how the core generates the magnetic field. It's based on the close relationship of magnetism to electricity. In particular, the fact that electric currents create magnetic fields.
Now, there's no electric current going through the coil to start with. The iron filings just go down like pepper in a pan, but if I turn on the electric current, then you can see the iron filings line up with the magnetic field that's produced by the current in this electric coil. So it's really currents inside the Earth's liquid metal core that we think gives rise to the magnetic field.
But what gives rise to the electric currents? The answer to that is where things get complex. Scientists believe that just as the electric currents produce the magnetic field, so the magnetic field produces the electric currents. The key is that the liquid metal in the core is in constant motion.
If you take a moving conductor in the presence of a magnetic field, currents get set up inside the conductor.
In the Earth, the moving conductor is 1 billion trillion tons of molten iron, but the effect can be seen in a simple loop of wire.
If I move this conductor in the presence of the Earth's magnetic field, then that gives rise to currents. Once you have currents, those give rise to magnetic fields. So it's kind of a curious loop that gets set up in the Earth's core. A little bit of magnetic field couples into the motion of the liquid, gives rise to currents flowing in the core. Those currents cause more magnetic field, which cause more currents, more magnetic field. So it's kind of a feedback loop that can cause the magnetic field to just rise.
If it works in the Earth, it should work in the lab. In theory, all you need is a bit of magnetic field to kickstart the whole process. It's not clear what exactly got the Earth's field started, but Dan uses a large electromagnet.
We apply a large magnetic field onto the sodium flow inside the sphere, and you can get a feel for how strong the magnetic field is. If we, Dan, turn on the magnets, we can actually see how they attract this chain quite strongly. Wipe out any bad credit cards you might have in a hurry.
If the electromagnetic dynamo theory is right, then the field generated by their miniature core will be stronger than the field they started with. The magnetism rapidly growing by drawing energy from the motion of the liquid sodium. It's something they haven't yet achieved, but already they have made one crucial discovery. What might cause a planet's magnetic field to fail?
Well, the different experiments that have been run have shown that a moving liquid metal is critical to getting the magnetic field to arise.
So if the core were ever to cool to the point where the liquid iron solidified and stopped moving, the dynamo would shut down. This may be why Mars lost its magnetic field so early in its history.
Because Mars is a smaller planet, it will have cooled more quickly than the Earth. So there's a very good chance that Mars has simply become too cold to sustain an active dynamo. It could be that the liquid metal core just froze out at some point.
But what happened to Mars must eventually happen to the Earth.
The Earth's core is very slowly cooling at the rate of perhaps 100 degrees per billion years. So eventually, the whole of the core will freeze. At that point, the dynamo will die.
Fortunately for us, the Earth's core is still well above the freezing point of iron.
The Earth's magnetic field has been around for a long time, at least 2 billion years. It has lasted so long because it has a very large energy source in the original heat that the Earth's core inherited when it was formed. And so the Earth can sustain the magnetic field for billions and billions of years of time.
So with enough stored heat to drive the dynamo for billions more years, it can't be a lack of energy that's causing our magnetic shield to disappear. There must be some other process at work far below our feet. The key to that process may lie on a chain of volcanic islands in the middle of the Pacific. Here, there's a magnetic record that goes back not thousands, but millions of years. It suggests that we may be about to witness not a gradual decline in the Earth's magnetic field, but a spectacular upheaval. Hawaii, where the heat that drives the core's magnetic dynamo reaches the surface. What's been discovered here may explain why the Earth's magnetic field is declining so fast.
All right, now I'm in.
For several years now, Mount Kilauea has been continuously erupting.
Well done.
Scientists from the US Geological Survey need to sample the lava to keep an eye on the volcano.
It solidifies pretty fast, as you can see.
But geophysicist Mike Fuller is interested in the lava for another reason. what it tells him about the magnetic field. It all begins when the lava hits the sea.
You can see the lavas having moved down from the volcano up here, sometimes in tubes, mostly in tubes. Now we're beginning to see it come out and go into the water and form the very newest bit of the island chain of Hawaii. As this lava hits the seawater, of course, it really chills very, very fast. And a very wonderful thing happens. They actually trap in, they record the Earth's magnetic field.
As they solidify and cool, these volcanic rocks are preserving a record of today's magnetic field. But the volcanoes of Hawaii have been erupting on and off for millions of years, building up the islands. Each lava flow contains a record of the magnetic field at the time of its eruption. So the Hawaiian archipelago is a hidden chronicle of the Earth's magnetism, stretching back 5.5 million years. That record shows there have been many fluctuations in the field's strength, but it contains something else of great significance. When the lava cools, magnetic minerals in it act like microscopic compass needles, recording not only how strong the field is, but also in what direction it is pointing. Today, the magnetic currents flow from south to north, which is why compass needles point towards the North Pole. And recently erupted lavas record a field pointing north. But when they examined rock samples from older lavas, scientists made an extraordinary discovery.
When we go back about 700,000 years, we find an incredible phenomenon. Suddenly, the rocks are magnetized backwards. Instead of them being magnetized to the north, like today's field, they're magnetized to the south.
It seemed that 780,000 years ago, Hawaiian lavas must have been cooling in a global magnetic field that was flowing to the south and away from the north, exactly the reverse of today. The bizarre implication was that at some point the entire global magnetic field had done a sudden 180-degree flip. The flow of the magnetic currents completely reversing direction. And as they examined samples from older and older lavas, scientists found more and more reversals. One on average every 200,000 years.
The last reversal was, what, 780,000 years ago. Before that, there was one about 200,000. Before that, again, actually less than 200. So in a sense, we are a bit overdue for a reversal.
So is this why today the field is getting weaker? Could it be getting ready to flip? Scientists needed to discover whether there was a link between changes in the field's strength and changes in its direction. Then one scientist unexpectedly saw a magnetic reversal actually happening on his computer. In the 1990s, physicist Gary Glatzmeyer decided to embark on a very ambitious experiment. He put everything that scientists had learnt about the Earth's molten core into a computer program. Then he let the program run to see how the magnetic field would evolve over hundreds of thousands of years of simulated time.
It's important to understand just how long these simulations take. Each time the computer solves the equations, it advances the whole solution one time step, and the time step is typically 10 days. And within 10 days, things don't change much, which means you have to do many, many solutions. You have to solve it millions of times, tens of millions of times in order to be able to simulate hundreds of thousands of years, which is what we needed. One case may take 6 months of running on the fastest computers in the world. So it was something I did every day, 7 days a week for over 4 years. And I remember there was a period of time, I believe it was in the fall, and I was traveling to other universities and giving talks, and after a number of weeks I came back and decided, well, now I need to look at the details of the magnetic field, and realized that it was in the reverse polarity. It already had reverse. This is something I didn't expect. So then I looked at many snapshots during the time I was gone and realized that the field did indeed reverse spontaneously. This is the first time it happened. We were very anxious to write about it. It was really exciting.
And as the experiment continued, so did the reversals. Every 100,000 years or so of simulated time. And crucially, each time the field reversed, the process began the same way.
What's interesting is whenever it has reversed its polarity, its direction, that happened when the magnetic intensity was very weak. So it was decreasing, decreasing. Finally, when it was the dipole part of the field was very weak, then the field reversed.
Here was the evidence that what we are seeing today, a loss of field strength, is indeed linked to the onset of reversals. What's more, Gary could see why reversals are heralded by a weakening field.
Now this movie will show part of a simulation that spans magnetic field reversal. What you see here, blue represents inward directed magnetic field, the gold represents outward directed magnetic field.
In Gary's model, reversals seem to start with the appearance of islands of blue in the gold, and vice versa. These are magnetic anomalies, regions of the core where the field is already flowing the wrong way. As they grow, these patches of reversed field start to cancel out the main field, making it weaker and more liable to flip.
You see, as the time goes on, the field becomes more and more complicated, and then you get an anomaly growing in the northern hemisphere where magnetic field now is going out. There is a reversal. Now the magnetic field is outward in the northern hemisphere and inward in the southern hemisphere.
So now the burning question is what's happening in Gary's model reflected in the real Earth? Is the 300-year decline in our field the work of magnetic anomalies brewing deep in the core beneath our feet? If so, then a reversal really could be on the cards. Amazingly, there are detailed records that cover exactly this 300-year period. The logbooks of Her Majesty's Navy. For as geologist Jeremy Bloxham has discovered, 18th and 19th century sailors were obsessed with the magnetic field.
Back in the days of James Cook, when he was doing his voyages of exploration, a compass was the primary means of navigation. However, a compass needle doesn't point at true north, at the real geographical North Pole. Instead, it points at magnetic north.
For sailors, knowing the difference between true north and magnetic north was a matter of life and death. But as they were well aware, the magnetic field keeps on changing as magnetic north wanders about near the pole. So over the centuries, navigators had to keep on measuring and remeasuring the angle between true north and where their compasses were pointing. The angle of variation.
The trick was to find true north, and they could do this by looking at the sun at noon when it's highest in the sky, alternatively by looking at the angle the sun made at sunrise or sunset.
Thousands of meticulous observations like these have helped Jeremy to construct a time-lapse movie of the magnetic field over the past 3 centuries. And it's what this reveals about one region in particular that's significant.
We've seen very abrupt changes in the Earth's magnetic field beneath the South Atlantic Ocean.
Beneath the South Atlantic, Jeremy has found the reason why our field has been getting rapidly weaker: magnetic anomalies. And they're growing.
As we get into the beginning of the 20th century, we see the emergence of a new patch of reverse flux, a region where the field lines, instead of coming out of the core, are looping back into the core. And that patch then drifts towards the west, hooking up with this other patch of reverse flux to create a large region, what we call the South Atlantic anomaly, where the field is about 30% weaker. And that patch has grown substantially during the last 100 years in particular. So one question we're all asking ourselves at the moment is the Earth's magnetic field about to flip?
Our magnetic field is weakening because part of it has already started to reverse. If it continues like this, then we could experience a magnetic phenomenon the Earth has not seen for 780,000 years. And that will have dramatic consequences for every person on the planet. There's a hole in the Earth's magnetic force field, and it's growing. Beneath the South Atlantic, the field lines are moving the wrong way, weakening our protective shield. Computer models suggest this could be just the beginning of the ultimate magnetic storm, a complete flip of the entire global field.
There's really no question about whether the Earth's magnetic field will reverse again. The question is not if that's going to happen, it's when that's going to happen.
Actually, in the last few hundred years, the intensity of the magnetic field on the Earth has been decreasing, which is an indication that maybe we're in for a reversal. The average time between reversals is on the order of a few 100,000 years. We're actually sort of due for one.
The human race has never been through a magnetic reversal. If we really are seeing the early signs of a flip, what exactly will happen next? Geologist Rob Coe may have the answer. He spent years investigating reversals.
First time I came to Steens Mountain was 25 years ago, and when we drove up to the top and could look down for the first time, we had no idea what we would see. Suddenly we were at the edge, and there was this magnificent panorama.
This is Steens Mountain in the western American state of Oregon. The mountain is a vast pile of ancient lava erupted in a dramatic burst of volcanic activity.
16 million years ago, there was a huge series of eruptions here. You can pick out literally hundreds of lava flows over on that wall. Each line delineates a different lava flow. It's over 3,000 feet of overlying flows.
What makes Steens Mountain special is that while these lavas were erupting, the Earth's magnetic field was in the midst of a flip. So Rob and his colleagues hoped that the rocks here might yield a uniquely detailed picture of the progress of a magnetic reversal.
The Earth's magnetic field is a mysterious thing. And then the idea that the global field could completely reverse, it's astounding. And I want to know more about it.
So Rob and his colleagues set out to sample dozens of flows all the way up the mountain. They found that the rocks from the lower slopes had been magnetized in a reversed field that pointed south But by the time the lavas near the summit were erupted, the field was pointing north. In between was a record of magnetic mayhem.
The actual reversal took several thousand years.
But what was really surprising was what happened to the field during this time.
What we found as it started to reverse was the strength of the Earth's field decreased dramatically by 80 or 90%.
As the field collapsed, it also started to behave erratically. For around 300 years, the direction of the field was constantly changing, eventually swinging a full 180 degrees to point north as the field strength started to recover.
But it couldn't hold that polarity, and it fell back to reversed, and the intensity crashed again.
Once more, the Earth's magnetic shield practically disappeared, this time for 3,000 years. What was left was changing so fast that Rob found a flow that captured these wild gyrations even as the lava cooled.
We came to this place right here, and this is the flow that we sampled. And what we found was even harder to believe. The quickly chilled margins in the bottom and the top had one direction, like that of the underlying flow, and the middle portion had a direction that was 60 degrees farther away. It was just as though, while the flow cooled, the field had moved 60 degrees, which if you calculate it out, that comes to about 6 degrees of movement per day. If we were observing this ourselves with a compass, you would be able to slowly track the field direction and almost see the motion with your eye. It was truly astonishing and extraordinary.
If the lavas of Steen's Mountain are anything to go by, the next reversal will mean centuries of magnetic chaos, with magnetic north changing direction from day to day. During this long period, the magnetic field will be too weak to be an effective shield, and that will have serious consequences for human health.
The intensity of the magnetic field will be weaker, maybe 10, maybe 100 times weaker than it is today, which means that more cosmic radiation will get through.
This basically opens our defenses so that solar and galactic radiation can hit the atmosphere directly. And this means that the radiation at ground level increases as well.
The estimate is that our overall exposure to cosmic radiation will double, and in some places it could be even worse. Today, the magnetic field focuses space radiation towards the far north and south, where few people live. But when the main field collapses, the weak field that's left will have a far more complex structure. Instead of just 2 magnetic poles, there may be 4 or even 8, slowly moving across the Earth's surface.
The structure of the magnetic field won't be the nice, smooth, simple dipole structure that we have today, which tends to deflect charged particles, cosmic radiation, to the poles of the Earth. Instead, there'll be several poles all around the Earth, maybe close to the equator. And so not only will the field be weaker, the field will tend to focus cosmic radiation at low latitudes where most people live.
This unfortunately means more deaths from cancer. It's roughly 15 per million people per year. That is the amount of deaths we're talking about. And if you multiply that over the whole population of the Earth, that becomes a significant number.
It's impossible to say for sure, but a reasonable guess is that every year 100,000 people would be killed by the increased levels of space radiation. Over the course of an entire reversal, the death toll would rise to the hundreds of millions. But of course this would still represent only a relatively small increase in the overall incidence of cancer.
So it's not going to be catastrophic, it'll be something to be concerned about, but it won't be a catastrophic event. And certainly by the time it happens, civilization will have figured out how to deal with it.
Scientists now know that at some point in the future, we will have to learn to live on a planet where only a few miles of atmosphere protect us from space radiation. But as our descendants wait for north to become south, they may find that a world without a strong magnetic field has its compensations.
The great thing is that it would be possible to see the aurora just about every night all over the Earth. So London behind me, for example, we might be able to see great aurora just about every night of the year, shimmering and moving in the sky as the solar wind hits the atmosphere directly, and it glows like a neon light.
Aurora would be very exciting. I can imagine a very interesting dynamic magnetic field outside of the Earth during the next reversal.
I would love to see a reversal happen, but it would involve me living rather longer than I planned to, but that would be very nice. In fact, it's one of the great tragedies of life. We never see how these things work out.
I'd really like to know how it does it and why it does it, and when will it do it again?